In this exercise, we're going to learn how to use the ping sensor. We're going to find the existing built-in file in sensors and go down to the bottom. We'll find ping, and we'll use that code to develop our exercise. And we'll put that over the top. So in this ping sensor code, let's take a look at it first before we run it. It says it uses ultrasonic rangefinder. That means it puts out a pulse and listens for it to reflect or echo back from whatever's in the environment. Listens for the return pulse. The length of the returning pulse is proportional to the distance of the object. Well, that just means that the time it takes for the reflection or the pulse to come back is based on the speed of sound, and it can determine just how far it is. And looks like this is some text that describes how to hook up our ping sensor to pin 7. Looks like this has been around a while. There's the setting to name the ping pin as pin 7. Looks like we're using the serial monitor. Let's look at the loop, see if we can follow what the code does. It sets the pin as an output, pings it or sets it low for 2 microseconds, then high again for 2 microseconds, then low again, and leaves it low, and then it turns it into an input and listens. And the duration from when it calls pulse in, time will go by, and that time will be measured. When that time is concluded, in other words, when this pulse in function thinks that a high enough signal of a pulse back has occurred, it will stop the clock and send the value back to duration. Then the code converts that by using another function, microseconds to inches, sending it the raw information that it just recorded, and another one that says it will get to centimeters by doing the same thing. Then it displays. Oh, and here's our code. So apparently, whatever the time is in microseconds, that the raw data, it divides it by 74, then by 2. Why by 2? Because the pulse goes out, hits the target, and reflects back. And that distance that's calculated by dividing it by 4 would be double. And all we want is the initial distance out. That's why they divide it by 2. And the same is true for centimeters. Well, enough with the code. Let's take a look at our circuit and get that hooked up. I have here 3 sensors, and from what we saw from the code, it's familiar with looking at a 3-pin ping sensor, and it has what I consider a standard pinout: ground, the center 5 volts, and the other pin on the outside, the signal voltage or the signal wire. But our kit, most of our kits, have 4 pins, and these pins have VCC on the outside, then trigger, then echo, then ground. And the 2 center pins, trigger and echo, for our circuit with our code, those have to be jumpered together or connected together as one common pin, and that goes to pin 7. And I have one more sensor. This one has 5 pins. I'm not sure what the output pin is for, except some output that we don't have code for. And once again, VCC. We have a trigger and echo, and at the far end, the other end, is the ground. So we will once again put a connection between trigger and echo and send that to pin 7. Well, we're going to use the 4-pin sensor today, and I want you to use from your kit the little breadboard. But before we connect that, let's look at our LCD platform. Make sure everything's connected correctly. We have our +5 or VCC and ground going slightly under the board onto this first set of rails for our breadboard. Around the other side, so the other set of rails are energized. We're following class conventions, which says that either black or brown or green is our ground. In this case, we're using a brown and red. So red is our +5 or our VCC, and that goes underneath the display, comes out on the other side here. But we also have 2 other wires coming from our display, and that is a gray and a white wire. If we were to turn this display over, we would remember that this end pin says SCL, which is serial clock. And our class conventions say that we're going to use the lightest wire, or white wire, for our clock wire. That means the next pin, the gray wire, must be serial data, or SDA. Well, it looks like our LCD is ready to go. I'm going to plug in this little, or snap on, this little breadboard. I'll plug in our sensor, and we'll make up a cable. Now, I don't usually advocate tying our wires into a nice tight knot, but today we will. We need to make something that's convenient for you and also convenient for the camera. So putting this nice knot in there allows these two wires to stay close together. And I'll plug those in the center two pins. Sometimes if it's a little stiff, just give the connector end a little twist and it should go in. I think I'll follow the same coloring pattern and plug into this next row and go to pin 7. Now remember, our connector is from 0 to 7. There's 8 holes. Always remember that this one is 7 that way. And that's done. But our circuit still needs plus and ground. Well, I believe that the voltage side is going to be on this side. This is our VCC. So I'll connect there, go on the end pin. And did I get that in the right one? We always have to look and see if the pin matches and lines up with the row, and it looks like it's off by one. Well, we'll just go over. Remember, all 4 of these pins will be connected to. So the next thing we'll do is we'll grab the ground and we'll connect that as well. There we are. And we can do that from this side. We have our ground rail there. We'll plug that in. And now I believe our ping sensor is connected. Let's go back to our code, and I will unplug and plug back in our Arduino. We don't always have to do that. I just think it's a good idea to make sure that the communication port isn't confused about what it's supposed to be doing. And I will check and see. Looks like mine is on COM11, and it is an Uno, so both of those are set. I should be able to upload this. I'll click the upload or press Ctrl-U, and it started. Now, do you remember that every time you open Arduino on your workstation for the first time, after you've logged in or reset your computer, that first compile, as it's getting other libraries and setting things up in its own program space, it takes longer to compile. After we make some changes, our compile will run a lot faster. Then it'll upload to the board. We'll watch our board flash, which is one of my favorite things to do, which we just missed. And then now it's the code is doing stuff. Now let's find out what it is doing. Click on the serial monitor, see if anything's showing up. Oh, and it is. So it has something it sees about 50 inches away. Well, you're not going to see this, but I'm going to hold a flat object out. Oh, maybe just over 2 feet. That looks like just over 2 feet, and as I bring it closer, the value gets smaller. Now, what's the closest we can get? Well, it says in the specs what the closest is, and I think it's like 2 or 3 centimeters. Let's see, when does it just not work well? Well, it seems to be doing well. There. Let's see if we can get these values to affect the brightness or dimness of an LED. We'll close the serial monitor, and I'll go back to the code. And in this exercise, when we do that conversion to change the brightness of our LED, we're only going to use the value that's recorded in centimeters. So I'm going to remove the code that has to do with inches. And I'll delete that, and I can delete this function as well. Now, it's not necessarily that we delete them, it's just that it makes our code a little cleaner and simpler, easy to see, easy to understand. So the first thing we need to do is figure out how to convert our values that we get back 4 centimeters. And what was that range? Well, it seems like the range, and I'll put it in comments so I don't forget. The centimeter range seemed to be from 0 to 140, 139. Well, I'm going to start it at, or stop it at 100. In other words, 1 meter. And we'll use that number range to change the values for our LED. Oh, but the LED, as you'll remember, when we change the pulse wave modulation code to send to it, it goes from 0 to 255. So let's find out how we can change or convert our numbers, because it's a ratio, 0 to 100 to 0 to 255 or 254. So do you remember the knob code? Knob, that's where I think it's in servo. So we go to File, Examples, Servo, Knob. Well, I have one open. We'll use that one next. Let's take a look and see what it did, because it converted the values generated by a potentiometer into values that our servo would use, which was 0 to 180. But we will use the map command, or the map code. So I think I'll just copy that code and have it as a reference. Control C, and paste our code where we can see it. So this is where it displays our values. Let's see if we can get it to also change the LED, and we'll put it right after this. So this is where a map would be. Control V. I'm just going to paste the whole line there. So our variable that's recorded the value isn't val anymore, it's cm. So do that. And our range of value isn't 0 to 1023, but rather 0 to 100. So I'll press delete twice, add a 0, that looks like 100. And the range for our LED is going to be, well, we'll start with 0 to 254. Now, what does this really mean? Let's take a look closer. It looks like when our distance is really close, the LED is going to be dark. In other words, there's going to be no, the pulse is going to be so narrow that you won't see any light. I think I want it to be lighter when it gets closer to 0. So I'm going to turn these numbers around and try that. It would have been just as much of a good exercise to have left that there and tried our code and see what it did, anticipating what it would do, and then changing it and getting what we actually wanted, just to prove that we knew what would happen. And this comment isn't true anymore. You'll need to update for your exercise, update the code before you turn it in to have the correct comments. So now we have centimeters is going to equal centimeters. Oh, wait a second, which is which? We're not converting centimeters into centimeters for value. This needs to be for our LED. So let's change that back to something we can work with. We'll call it LED duration. I wonder if I can get away with making those lowercase. That actually looks better. Okay, so we're ready to compile. Or are we? I just created a new variable. Control C. I think I better go up here and declare that. So it's going to simply be an int, an integer. There's our variable's name, and it doesn't have to equal any particular value at the beginning, but we should comment and say what it is. And we'll call it a ratio. Okay, I don't think we've broken our code yet. Now sometimes when I'm changing code, especially if it's getting complicated, every once in a while I'll check this, just to, not that I need to export it, but just to see that I haven't had a typo. I don't want to change a lot of code, then compile it, and have one error make another section of code look like it's wrong and end up troubleshooting in the wrong area. But I think this code is ready to go, so I'll export it. Hit the upload. This time we'll actually watch our code come in. Once I fix the inches duration, it looks like we called for the subroutine. It doesn't exist anymore. We deleted it. And just a reminder, you remember, when an error occurs, you always go to the first error that you can see. So it's telling us that this was not declared in the scope. And it's telling us even what line it's in. So we can delete that. And we'll upload, switch to the board. This time our compile should go a lot quicker. It's uploading. We can see the data flash on our card. And now we should see on our serial monitor our centimeters showing up. That's true too. Oh, but maybe we should see that value that has to do with what we're generating for our LED. Well, let's do that next. We'll add that to our code. And how do we get that out? It looks like we use a serial print. This is still going to be the last serial print, Control X. So I'm going to move it down here right below where we generate our new value. And we'll line it up so it looks good. And we'll just copy this code up here. And change this to be, well, LED duration. Control C. There we go. Control V. I'll paste it there. And I want a space between that value and duration. And then it prints a blank line and starts over. I think we're ready. Let's try this again. We'll export it, upload it, watch the data show up. I like to see that. Looks like progress. Then go back to our serial monitor. So it looks like for the 130, 140 hour LED, now that is as far away as we can get. I'm going to tilt this up, see what our numbers are. I think I can see both. Let's try that. There we go. Now by tilting it up, what that means in my lab here is that I'm pointing it into open space. And so we're in the upper 90s. Now we can tune this. Tune this means adjust it to what we're really seeing so that it picks a lower value. So I would expect this to be 100% in the LED duration. Let's try shorter. So if I again bring my space in, my shape in, that it can reflect off of. Looks like it's going down. Oh, it's getting brighter. There we go. So when it gets down to here, I think I want it to be completely on when it gets down to 7 or 8 centimeters. Okay, we'll close that, get back to our code. We need to go right to changing the brightness of our LED and see what that looks like. So let's add that circuitry. Okay, for this exercise, I'm going to use a 3-color LED just because I have one. And I have a resistor whose legs are too long, so I'm going to cut it off. And I am holding my cutters what would be considered upside down on purpose. The reason is if I cut them this way, instead of leaving a flush cut to my pin, it actually makes it wedge shaped, which I think will go into this board a lot easier. So I've picked this, I'll place it on this end pin there, and I'm using a 330 ohm, and get a wire to connect my LED. Well, I've been working on my circuit. I have the analog connected to the pin 6 output connected to the resistor going into my LED, and then the anode of the LED going to plus volts, VCC, +5. Okay, so let's take a look and see what this does. We'll need to add some more code. So I have my map, and down here I need to write to my pin. So I've put in some of the code already up here. In this setup, I've made it so that pin 6 is the output. That's what I'm going to use. And the reason I chose pin 6 is I needed to pick a pin. Let me get where you can see that. There we are. I need to get a pin that was pulse wave modulation. Now, let's see if we can get the focus. There we are. Notice that little squiggly line in front of pin 6? That's a tilde, that's a character, and that implies, or it tells us that that's a pulse wave modulation. You can see it in the silk screen. Okay. So now if I'd used pin 4, it would have just turned off on and off, on or off, but nothing in between. So enough of that. Let's get our circuit to work. So everything is plugged in there. Let's go back to our code. In our code, we've got the output, got the conversion, got the numbers. We've created the value, corrected the value. So let's write that out. We'll just copy what's in there already. We have up here where it says digital write. Yep, that's what it says. So let's copy that pattern. D-I-G-I. And parenthesis, this is 6, pin 6, and LED duration, and close, and oh, but it's not orange. It's not a command yet. Probably because we forgot to make that a W. Now, there we are. Let's see what this does. We'll upload that to our board. So there it is. And I'm changing the distance and nothing is happening. Well, apparently that command we used wasn't the right one. Let's go back and look. Well, check our serial monitor. I can see the values are there when I'm close to when I'm farther away. Well, that seems to be okay. So what's going on here? Well, it seems like if we want this value that's going out to our LED to be changing, in other words, actually changing that pulse width, we need to make this analog. Because digital is just simply on or off. So, analog write. Let's try that. Control U. Okay. And serial monitor, display. There, that works. So, as I get farther away, it gets brighter. Oh, wait a second. If I get closer, it gets dimmer. I know it's hard for you to tell. The LED's right up here. I did try to put some black behind it. That's opposite of what I wanted, and actually opposite what I expected. This is a high number. This high number I thought would make it brighter. Oh, if this were the on time, but we have a circuit that inverts that. Well, invert, that means make it the opposite. So if the plus volts is supplying the VCC or pin 5, then when pin 6 is low, then it's on. And when the number is high, it's going to be low a very short duration. In fact, you can take 255, subtract where this number is, and that's how long it's going to be low, or that's how long it's on. So it's almost like a double negative. Well, not to worry. We'll just go back to our code and make an exchange. Change this from 254 to 0 and 0 to 254. Okay. We'll export it, see what happens. Now it really is upload, but you know from my work in class that I use other applications where export is the command, and so I get them backwards. I do know that it's upload. Okay, so we'll switch back over to our board after we turn on the serial monitor. Okay, so it's close, it's bright. As I take my hand away, or my panel, where's my flat panel? There it is. And as I pull it away, the number gets bigger, LED gets dimmer. Well, maybe we should put some kind of a limit so that this can't go out of range. And you know what? I'm going to leave that for you to do. So what we have done, is we made it so when the distance changes, when the ping sensor sending its pulse out and is reflected back is converted into centimeters, and then those centimeters are mapped to become a ratio of brightness for our LED. We can make it dim or bright. We can control our LED. Now, if this were a two-color LED, well, it is a three-color LED. If we were to use that inversion that we saw a moment ago on a different color, so instead of going from bright to dim, it goes dim to bright, then the two colors would exchange. And that might be cool to look at. Well, this concludes this exercise. Hope you enjoyed it. Good coding.